vapor pressure of liquid-liquid solutions. See, whenever we are mixing two solutes, in this case particularly both the solute and the solvents are existing in the liquid state. When a liquid solute is added to another liquid solvent, what happens is, what we observe generally is that the vapor pressure of the solution formed is found to be more than the vapor pressure of the original solvent. What we find is that the liquid solutes taken are volatile. In fact, both the liquids, the solute and the solvent, are volatile. It means they can easily evaporate to the vapor state and are taken, the liquid solutes taken are volatile when added to the liquid solvents. Vapor pressure of solution, which we call as PS, is found to be more than the P naught A. What is P naught A is? Vapor pressure of pure solvent when the solvent is present alone. So what we find is, whenever a liquid solute, since see, when the solute is liquid, it means it is already not having very high boiling points. So it's volatile. When added to a liquid solvent, the vapor pressure of the solution formed is found to be more than the original pure solvent. So it gets increased. It can be explained by taking an example. Like, we were having originally a liquid solvent A, to this what we have done is B liquid volatile solute has been added. Now what we find is, now the vapors of both A gaseous and B gaseous. That means now the vapors of both the components are present in the vapor state, in the gaseous state. Now since these vapors of both of these components are present in the gaseous state, we have more number of vapors, more number of molecules in the gaseous state. As a result, the vapor pressure of the solution, the PS, is found to be more than the vapor pressure of the solvent in the pure state. It gets increased. This increase in the vapor pressure of the solution was studied quantitatively by a scientist called F.M. Royals, who gave a famous law which is called Royals' law for the solutions having volatile solutes. Now, according to this law, which is called Royals' law for solutions having volatile solutes, the vapor pressure of a component is proportional to the its mole fraction in the solution. The solutions having volatile solute, in such solutions, The vapor pressure of a component is always proportional to its mole fraction in the solution. This is the basic of the Royle's law. Now we can find out the formulas on the basis of this law. Like suppose this solution is having A and B, two components. A, as usual, is your solvent. B is the solute added. We know from the Dalton's law of partial pressure, since molecules of both A and B will be there in the gaseous state, the PS will be equal to PA plus PB. What is PS is vapor pressure of solution. What is PA and PB are partial pressures of A and B. Now, Royle's law states that as per Royle's law, as per this law statement, the partial pressure of any component is proportional to the mole fraction of that component in the solution. So what is XA is? XA is the mole fraction of A in the solution. And this proportionality is opened by a constant which is called P naught A XA. Whereas what is P naught A is? It's the vapor pressure of A in the pure state when it is present alone. Similarly, the partial pressure of B will be proportional to the mole fraction of B in the solution, and it will be opened as this PB will be equal to P naught B XB. So it is like this, whereas what is P naught A and P naught B are? P naught A is vapor pressure of A in pure state when it is present alone, whereas what is P naught B is? It is vapor pressure of B in pure state. So same situation. So it's the same thing. So what we find is P naught A is PA is equal to P naught A XA and PB is equal to P naught B XB, whereas XA and XB are the mole fractions of the A and the B in the solution. So we can have this equation, this major equation of finding out the vapor pressure of the solution can be written as, we can write this equation as PS is equal to XA P naught A plus XB P naught B. So it's like this. So this is one form of the expression of finding out the vapor pressure of the solution which are having volatile solutes. We can change this expression into another form, like we know XA will be equal to 1 minus XB, because we know the sum of the mole fraction of the components of a solution is always unity. So XA is equal to 1 minus XB, and we will replace the value of XA by this one. So what we get is PS is equal to 1 minus XB, it's P naught A XB P naught B. We can take out P naught A, and what we can do is we can add this here. We can take P naught XB as common. What we get is, in this case, it is P naught B minus P naught A. So this is another way of writing the same equation, but this gives us a very clear-cut idea that P naught A was the vapor pressure of the original solvent, pure solvent, before forming the solution. The moment we add a volatile liquid solute to the same liquid solvent so that the liquid-liquid solution is formed, what happens is vapor pressure gets increased, which is PS. How it is increased? We are adding something to this value, which is actually the product of XB and the difference of P naught B minus P naught A. This is what it means that PS is greater than this P naught A. How much? By this value. So this equation gives us clear-cut idea that the vapor pressure of the solution gets increased. Yes, we can draw the graph on the basis of this equation by comparing this equation with y equals to mx plus c, which is an equation of a straight line. Now let us draw a graph from this formula by comparing it with equation y equals to mx plus c, which is an equation of a straight line. Now the graph drawn is called px diagram, or it is called vapor pressure mole fraction diagram. It's called px diagram, vapor pressure mole fraction diagram. What we do in this case is, the graph drawn is almost as like this. Vapor pressure are taken on both left and right hand side of this graph, and along x-axis mole fraction is taken. On the left hand side, mole fraction of solvent is taken as 1, whereas of the solute is taken as 0, whereas on the right hand side, mole fraction of the solvent is taken as 0 and of a solute is taken as 1. This is what we have is called P naught A. This is what is called is P naught B, and this is how this graph comes out to be at the end. It's a straight line. Now this graph is for the PS. See, one has to understand this graph. The x-axis is indicating what? The mole fraction, the composition of the mixture. The y-axis are having the vapor pressure. The left hand side is having pure solvent, the right hand side is having pure solute. Now suppose these lines are indicating the vapor pressures of the individual component. When the solvent is taken in the pure state, definitely it will be having the pressure which is equal to P naught A, this value, and when the solute is taken individually alone, its vapor pressure is called P naught B, vapor pressure of the B in the pure state. Now suppose you are having already a solvent in the beaker. Already this beaker is having certain solvent A. Now to this we are adding what? B. When B is added to this, what happens is, when the A was present alone, its mole fraction was 1. The moment you start adding B, and initially the mole fraction of B was 0, but the moment you start adding B, what happens is the mole fraction of A decreases and of B increases. It becomes suppose 0.9 and suppose it is now 0.1. Then what we find is, already the vapor pressure of the solution was P naught A. The moment you put now the B into this, it gets further increased to a certain value. If we can draw a parallel line to the x-axis, what we find, this is what is increases. You keep on adding more of the B, the vapor pressure keep on increasing because B is having a higher what? Vapor pressure. So it keep on increasing. And as the composition of the mixture changes, it is becoming more and more rich in the B. What we find, the vapor pressure is also increasing. We can reach to a situation where we can have only a B, almost A is negligible. Then the vapor pressure of the solution will be equal to what? The vapor pressure of the B in the pure state, which is P naught B. So these are the extreme ends possible, and this from P naught A to P naught B is a situation which is called the solution, and this straight line is indicating the vapor pressure of the solution. The best part of this graph, you can, from any point you can draw a perpendicular, you can find out that what will be the composition of the solution at that particular vapor pressure. And we can find out in the liquid state how much of A is there and how much of B is there. So this is what is the graph is, and as indicated by this graph, the slope is positive. It's actually the slope is P naught B minus P naught A. This slope is P naught B minus P naught A. Intersection is at P naught A. Intersection is at P naught A. So this is what is your PX diagram is, and the solutions, which actually in all those solutions in which the PX diagrams comes out to be like this, are called ideal solutions. Or what we can say in other words is, all those solutions which follows Royd's law and their graphs are coming out to be like this, a straight line, they all are called ideal solutions. From this PX diagram, we can also make out certain one or two very important things. The first, the vapor pressure of the solution is varying linearly, actually linearly with the composition of the solution. The vapor pressure of the solution can be correlated with any of the mole fractions of A or B, because it can be correlated with respect to A or with respect to B. These lines which are drawn dotted actually are indicating the partial pressures of individual component. If we are taking, like in this case, if we are starting from here, we were knowing there was no B. The moment we started adding B, its vapor pressure slowly increases and it can reach to the maximum of P naught B. So it is this line which is actually indicating the partial pressures of the B. Similarly, if we are starting from this point, we know that here we are having only the solute, not the solvent. So if we keep on adding A, its the vapor pressure will increase from 0 and can go up to the maximum value of P naught A. So these are the significance of dotted line is this. And another important thing is that the vapor pressure of the solution you can consider with respect to A. If the solvent is taken as A, with respect to B it is increasing, and with respect to B, if the B is taken as solvent, it is decreasing. So like this. So it varies the vapor pressure of the solution according to the composition or the mole fraction of the solvent, one component in the solution. So these are the things which you can easily make out from this graph. Let us try a numerical on these type of solutions. Let us see with the help of a numerical how the Royd's law can be used to find out the vapor pressure of the solutions, actually which are liquid-liquid solutions. Find the vapor pressure of the solution having 50 grams of benzene and 50 grams of toluene. The vapor pressure of benzene and toluene in pure state are 400 and 300 mmHg respectively. So we are given that the vapor pressure of benzene, B means benzene, in the pure state is how much? Is 400 mmHg, and that of T I am taking as a symbol for toluene, as it is 300 mmHg. We also know benzene as C6H6. So its mass is how much? 12 6 are 72, and this makes it 78. So the number of moles of benzene will be 50, the weight of benzene upon molar mass of benzene, which is 50 upon 78. So which is 0.64. Whereas toluene is C7H8. So the number of moles of toluene will be weight of toluene upon molar mass of toluene, which is 50 upon 12 sevens are 84, and 8 makes it 92, which is 0.54. Now these are the number of moles of the things we have, the two components we have. So what we can make out is mole fraction of toluene will be number of moles of toluene upon number of moles of benzene plus number of moles of toluene. So it will be 0.54 upon 0.64 plus 0.54. This is 0.54 upon 1.18, which comes out to be approximately 0.46. Approximately 0.46. Whereas what we find is if mole fraction of toluene is 0.46, mole fraction of benzene will be 1 minus mole fraction of toluene, 1 minus 0.46 is 1 minus 0.54. So once we know their number of mole fractions, we know that the PS is equal to what? The partial pressure of benzene plus partial pressure of toluene, which will be mole fraction of benzene and the vapor pressure of benzene in the pure state, mole fraction of toluene and the vapor pressure of the toluene in the pure state. So it will be XB, benzene's vapor pressure is 0.54 into is how much? Is 400 plus 0.46 is into 300. So this will be 4 4 16. It's 216 plus 138. So it's 354 mmHg. So this will be the vapor pressure of the solution when this benzene and toluene are mixed like this. We can use this formula, the modified one, from which we have got the px diagram also in place of this formula, and we can find out the same answer. See, the formula was Ps is equal to P naught A plus Xb of P naught B minus P naught A. A was the solvent and the B was the solute. Now in that case, B was a volatile solute whose vapor pressure was more than the A. Now in this case, out of benzene and toluene, benzene is the one which is having a higher vapor pressure. So our B will be the benzene, same with B symbol, but our A will now become the toluene which is having a lower vapor pressure. So I will replace A by T. So the formula becomes Ps is equal to P naught T plus Xb P naught B minus P naught T. And we know the vapor pressure of the toluene in the pure state is 300. Mole fraction of the benzene in the solution is 0.54, and the vapor pressure of the benzene in the pure state was 400 minus 300. It comes out to be 100. When multiplied by 0.4, it gives you 54. So 54 plus 300 is already also 354. So we get the same answer. So we have an option of either using this formula, the modified one, or we can use the same formula, the PS is equal to P naught A plus PA plus PB. We can use any one of these formulas to find out the vapor pressure of the solution.